commence. Okay. Hello, everybody. Welcome to the third day. We continue with lectures by Isabelle on composition operators. Isabelle, please.
Thank you, Gerard. So for the last lecture, we will have an answer to the questions we had, I think, at the end of the first lecture, or maybe the second. So the question was, can we deduce the limit of when t tends to infinity of c phi t? So it's very special semigroups. It's composition operators, provided there are C0. Can we deduce the limit from the generator, that is a data at 0? So I remind you that, okay, we have an analytic semiflow on the open-ended disk. Then we have a notion of generator for this semiflow defined by J. So G is the limit of this, and it happens that it's an holomorphic function on the open-ended disk. This was proved by Bergson and Porta, as mentioned in several talks before. And the link between the generator of the composition and the generator of the semiflow is the following. I call it A, and AF is completely determined by G, because AF is GF prime. And from this, we can see that the A is not bounded in general, because its domain, it's not the whole space. Because in many spaces, when you take an f, its derivative is no more in the space, and provided you multiply by g, the same. It's not true. It's not evident that it's not obvious that this will stay in the right space. But at least, provided it's a C0 semigroup, domain is dense. Okay, so first I will remind you or mention, for people who are not familiar with that notion, well-known properties of analytic semiflows. And I would like to make a recommendation about a very nice book, a recent book written by Filippo Bracci, Contreras, and Diaz Madrigal, about continuous semigroups of holomorphic self-maps of the unit disk. It's a very nice book where all the things I'm mentioning today are very well detailed, and many other things inside. So very, very nice book. So the first thing is that for all t, phi t is automatically injective. This is important, for example, if you consider composition operators, semigroups of composition operators on the Dirichlet space, for example, because in this case, because phi t is injective, C phi t is well defined. A second observation is that if for some t0, it happens that phi t0 is an automorphism, or even an elliptic automorphism. That is an automorphism with a fixed point inside the open-ended disk. Then it happens that all phi t is of the same kind of functions. So all the phi t are automatically automorphism, and if one of them is elliptic, all the others are elliptic. And moreover, for all semiflows which are not elliptic automorphism, there is a unique point in the closed unit disk called alpha as previously, such that you have the limit of phi t minus this point when you take the subnorm on a compact subset of the open unit disk. It tends to 0. So that's the so you have we already know that. Okay, just make remark for T0 fixed. We know that this is equal to phi n T0, okay? And it happens that, sorry, it's composition by phi n T0. And from the Dangerous theory for just one composition operators, we know that this guy tends to one point called alpha, that this alpha may depend on the point T0 you have chosen. But the Dangerous theory for semigroups says that it does not depend on the T you take. In fact, it's independent of the choice of the T0. Okay, so now this such alpha is called the dangerous point of the semiflow. And then I remind you a result already mentioned by Wolfgang Arendt yesterday. He mentioned Bergson and Porta result, which is the following. If you have an analytic semiflow on the open unit disk, then the generator exists for all Z. And moreover, we have a precise form of its generator. And the form is the following. It's an alpha, which is precisely in the case where phi t is not made of elliptic automorphism. This alpha is not the wrong notation. That's really the same as the dangerous point of phi t. So it's alpha minus z times 1 minus the conjugate of alpha times z times a certain function f, which is holomorphic and for which the real part is non-negative. In fact, because f is holomorphic, if f is not constant, the real part will be strictly will be positive, in fact. And oh, sorry, I have okay. Oh, thank you, Javad. Javad gave a link to the book of Filippo and others. Thanks. Okay. So in particular, when you have a function with such condition, it happens that it is automatically in the intersection of all the Hardy space for p less than 1. And in particular, it implies that such f has a radial limits almost everywhere. So the G has all the same property. It has radial limits almost everywhere. And Bergson and Porta proved that also that reciprocally, if you have a G of this form with an arbitrary f satisfying this condition, then it is the generator of a semiflow. So we have a complete characterization of the generator. And this characterization, at least when the phi t are not elliptic automorphism, involves the dangerous point of the semiflow. I would like to mention another characterization of the generator of the semiflow that we obtained in a joint work with Corentin Vicou, one of my PhD students, and Jonathan Partington in 2015. We proved that another characterization of generator semiflows is in fact to be holomorphic, having radial limits almost everywhere on the unit circle and on the unit circle. And here I mentioned, I consider the radial limits. That's in this sense that I write this. because obviously G is not defined on the closed unit disk in general, but at least it has radial limits. And so another characterization, avoiding the Dangerous point and the F and so on, is the real part of the conjugate of Z, G of Z, is non-positive almost everywhere on the unit circle. Okay. So now we will use the result I have presented yesterday. I will restrict myself to the Hardy space, but okay, we can get the same result for other spaces. We mentioned that later. So I have mentioned at the very end of the talk that the existence of a P, such that P is the limit of the composition operators to the n. So I just take one composition, not semigroups. That's the discrete case. And I mentioned that the existence of a limit for the topology of the norm is equivalent to the fact that you have a limit for the strong topology. There is no difference. And the criteria is the following. The symbol of the composition is not inner, and the phi has a fixed point inside the unit disk. Okay. And the reason for that is, well, if phi is inner with a fixed point, it happens that C phi is similar to an isometry, so no way to get a limit. Okay. So from this, we obtain the following result concerning semigroups. We take the Hardy space, but what I mentioned is true for other classical Banach spaces, such as Dirichlet space, Bergen spaces. And this is the following. In fact, the semigroup strongly converges to, well, a projection of rank 1, if and only if the same is true for the norm. And we can characterize that in terms of properties of the generator, that is the generator G, the generator of the phi t, which is nearly the same as having the generator of the semigroups, because the A of this one, the A which generates say phi t, is defined by this expression. So having A is equivalent to having G. So we have the convergence in the strongest topology, or in the or for the strong operator topology, even only if the G has a 0, and we can find a Borel subset of the unit circle of positive measure on which the real part, so this quantity must be understood in the sense of the radial limits, and the real part is a negative on this non-trivial Borel subset of the unit circle. And just a few words to explain why we have that. Okay, so the fact that G has a 0 in D means exactly that the alpha in the description of G given by Bergson and Porta, which is the good candidate for being the van der Waals point of the semi-closed, provided it's not an elliptic automorphism, is inside. Okay, so we have this equivalence. Therefore, phi t is an elliptic automorphism for all t, or it is not the case. And in this case, the Blanche-Arpels point is in D, which is the criteria we have. Okay, now let's look at the second condition. We require that the real part of this is negative on a non-trivial Lorentz subset of the unit circle. It happens that this is the way to express the fact that the semiflow phi t is not made of automorphism. Indeed, if phi t is if I have automorphism, so it's not just a semiflow but a flow, and if I have a semiflow or a flow of automorphism, it happens that G on its opposite minus G generates semigroups. So the real part of Z bar G is negative and is non-positive, and on the other side, the real part of Z bar minus G is also non-positive. So the real part must be equal to 0 almost everywhere on the unit circle. So the way to say, so here it's an interpretation of that is just to avoid case of automorphism. Okay, so it means that with this and this, we have cancelled the case of elliptic automorphism. And why is it equivalent to the existence of a limit? In fact, I mentioned at the very beginning that for all the semiflow, they are automatically injective. So now our criteria were the symbol is not inner, but if you are not inner and injective, it's then equivalent to be not an automorphism. Okay, so you see that the work in the discrete case provide the answer for the semigroups. And in this case, we are very lucky because we have a characterization of the existence of limit from a data at 0 that is from the A or G. Okay, so it's that's the end of the biggest part of this lecture. And now I will go slower. I wanted to be absolutely sure to have finished this part. So now I will leave the case of the open unit disk to study what happens for the asymptotic behavior of composition operators, but on other domain. So I would like to replace the open unit disk by the whole complex plane. And I would like to look at composition operators on quite well-studied spaces of entire function. That is a Fock space. And I'm interested in the same properties, namely the asymptotic behavior of C phi to the n, or the description of what happens for semigroups of composition. Okay, so this work is a joint work with Jonathan. We had in this summer. It's our first 100% Zoom paper. It's quite sad, but okay, that's life. Okay, so I will start slowly with the definition of Fock spaces and so on. So for a parameter mu finite between and greater or equal to 1, the Fock space f nu consists of entire function such that the following interval is bounded, is finite. So I take f, the modulus of f to mu, and I put an exponential en. And this is all that to the power of 1 over mu. Okay, we can give other more generalized Fock spaces changing with this thing, but okay, we will stay in this kind of Fock spaces. Okay, so we have the norm, and this is a Banach space. In fact, we can even say that for nu equal to 2, we have a Hilbert space. And it's a classical fact that, in fact, when you take e z to the n over the square root of factorial n, this is an autonomous basis. Okay. And we would like to consider composition operators on both spaces. And this was the study. So we would like to study composition. And we would like to know first for which phi is it well defined. So we would like to characterize phi such that C phi is bounded. It was done in 2003 by Carswell, McLauer, and Schuster. And what they did is, in the case of F2, they characterize the bounded operator on F2, the bounded composition operator. As follows. So they prove that C phi is bounded on F2, if and only if there are just a few phi for which it's possible. The phi is of the form AZ plus B, where the A must be of modulus strictly less than 1, B is an arbitrary complex number, or the phi is just AZ with the modulus of A is equal to 1. And moreover, in the case where the modulus of A is strictly less than 1, it happens that C phi is compact. Okay. Okay, so in fact, this result was then generalized for weighted composition operators and with arbitrary nu between 1 and infinity. But okay, this pioneer work is very important in this theory. Okay, maybe. Okay. Okay, the same. Well, later there was some generalization. Then, oh. Then other people were compass subject. For example, in 2014, Lei, and even in 2016, I and Coy. They studied weighted composition operators W defined by WF composed with phi on the Fock spaces general one. And they proved also that so they can characterize completely when this is bounded. And in any cases, phi must be of the form, the same form mentioned by the pioneer work of Carswell, McLauer, and Schuster. Okay, so even for that, there is no choice. This, for any weight, so in particular for a weight equal to 1, this is bounded, implies that the symbol must be of the form AZ plus B with this condition. Okay, I think I will not have time enough to consider weighted composition operators, even if we also studied them, and we also studied their asymptotic behavior, but I will stay with the case of unweighted composition. So, composition. Okay. So, as previously, let's start with the case of the discrete case. So we begin with the study of the powers of 1 C phi. So discrete case. So we would like to study the asymptotic behavior of that. Now C phi to the n, because the phi is so simple, it's easy to describe. C phi n is just f composed with a to the n z plus 1 minus a n over 1 minus a b, provided a is not equal to 1. Okay, and so this is that, or this is just the identity map if a equal to 1, because in the case where the modulus of a is equal to 1, b must be 0, so that C phi is well defined. Okay. And to study the asymptotic behavior of that, once more, we use Nagel's result I mentioned yesterday. So to that aim, we first need to check that C phi is power bounded. So to that aim, the first thing to do is to check that C phi is power bounded. Okay. But we have an estimation of the norm of C phi. That's also a work initiated by Carswell, McClower, and Schuster in the case nu equal to 2. And then, so it's the same paper. And then generalized in 2019 by Dye. We have an estimation of the norm, which is independent of the parameter. C phi, the norm, is in fact equal to the exponential of 1/4 the modulus of B square over 1 minus the modulus A square. If at least phi is AZ plus B with A strictly less than 1. Okay, so when we look at C phi to the n, because we have still a composition operators, C phi to the n is now a composition by this function, A to the n, and the B is replaced by this. It's easy to check that it's power bounded, at least for the modulus of A is strictly less than 1. So now I put the theorem. So the asymptotic of iteration of bounded composition operators on Fock spaces is as follows. Okay, if phi is equal to AZ with the modulus of A equal to 1, and we avoid the trivial case of the identity map, then in this case, C phi n consists of unitary operator. So it does not converge even weakly. So the most interesting case is the case where phi is equal to AZ plus B. Then C phi n converges in the strongest topology. So in the converges in norm. in operator norm to the evaluation at B over 1 minus A. Okay. And now we do the proof. Okay, in the first, if phi is just AZ, where A is modulus 1, take the identity map. So C phi n is just f of a n z, and it's then equal to a n z if, so we avoid the trivial case a equal 1 if you take the f of z equal to z. Okay, so it doesn't converge even weakly. Okay, so more interesting is the other one. So assume that we have AZ plus B. Okay, and C phi to the n is C phi n, where the iterates of phi is just a to the n plus 1 minus a n over 1 minus a b. And so that's our new, so this is called an, and this is our new bn. Okay, and we know from the expression of the norm that when we look at bn square over 1 minus an square, because it's not, it's in the previous slide. Okay, see that the norm of C phi is exponential of something like that. So you just have to compute b to the square, 1 minus a to the square. It's easy. And you see, because of the expression you have and the fact that a is greater than 1, it tends to b square over 1 minus a square. Okay, because am I right? Yes, okay. Is tend to 0, and bn square tends to that. Okay, so it's power bounded. Now, since C phi is compact, the essential spectral radius of C phi is 0. And in the Nagel's theorem, we require that the essential spectral radius is strictly less than 1. Okay, now the other conditions concern the point spectrum. So for the point spectrum, suppose there is an eigenvalue. And f an eigenvector. Okay, so so such that f of az plus b equal to lambda f of z. Iterate, we get f of a n z plus b 1 minus a n over 1 minus a is then equal to lambda to the n f. So that is, so it implies that lambda n f tends to f at b over 1 minus a for any z. And it follows that f is 0 if lambda is equal to 1, but lambda equal to, so f must be 0 if the modulus of lambda is equal to 1 and lambda different from 1. Okay. So finally, if 1 is in the spectrum of C phi, then 1 is in the point spectrum of C phi, since C phi is compact. Okay, and by this equation, in fact, the only eigenvector is constant. So f is constant if f is an eigenvector associated with 1. And so the dimension of the kernel is 1. Is one-dimensional. So 1 is the pole of the resolvent of order at most 1. Okay, and then we apply Nagel's theorem we have seen yesterday, and it happens that C phi n converges to a rank 1 operator, converges in norm to T defined by Tf equal f evaluated at b over 1 minus a times 1, the constant function 1. Okay, so as you see, the point is that the phi for which C phi is well defined on the Fock spaces, they are quite limited, and applying Nagel's result, we get the asymptotic behavior very easily. Now let's have a look to the semigroups. So we have done the discrete case, and now we are interested in semigroups of composition operators. Okay, so take the color red to show you the result. So in fact, a semigroup of bounded composition operator on Fock spaces satisfies one of the following conditions. So first case, the phi t must be of the form exponential of lambda t z plus a certain constant c exponential of lambda t minus 1 with the condition that lambda is in C minus, defined to be the complex number for which the real part is negative. And sorry, so the lambda must be like that, and the C is arbitrary. Or the other solution is just that phi t is exponential of lambda t z for some pure imaginary complex numbers for some lambda in R. Okay, so still the cases of it's limited just a few semi-flows for which we have the boundedness of composition operators, and the generator is given by AF equal lambda Z plus C F prime, where C is equal to 0 in case 2. Okay, and in this case, TT, so C phi t converges in norm as t tends to infinity, even only if lambda is in C minus, and it converges in norm to t, the function which is the evaluation at minus c. So this is an obvious consequence of the discrete case. So the only thing to do is to check that there are, in order to get a semi-flow in the family of function of the form az plus b, that's you have just those cases. So it's not very difficult. And to conclude, so not so the proof is just obvious from what I mentioned previously. I would just conclude this talk with an application of the result already mentioned several times by Eddie Bernard and also by Wolfgang. Concerning the semigroups generated by a generator which has a special form. So what we get is that every C0 semigroup, well, I just restrict myself to the Fock spaces, which is a Hilbert spaces, Hilbert space. So every C0 semigroup on F2 with a generator of the form AF equal certain function f g f prime for some g, an entire function. So every C0 semigroup on F2 with such generator is automatically a semigroup of composition operator. The G has the form AZ plus B with the real part of A negative or G equal to AZ, where A is pure imaginary complex number. And moreover, we can get another characterization of generators of semi-flow generated C0 semigroups of composition. So it happens that G has the form AZ plus B with the real part of A negative, or if B is non-zero, or A in RR and B equal to 0, if and only if. And we will recover the result we have found in a joint work with Corentin Vicou and Jonathan. It's equivalent to say that the limit when the modulus of Z tends to infinity of the real part of Z bar G is not positive. So you recover exactly the same kind of criteria, which was the characterization of generator of semi-flow on the unit disk, but here it's on the whole complex plane, and you see that you tends to the boundary. But in this case, so what is the analog of Baxton and Porta result? It's even much more simple, because the semi-flow are just a few in this case. Okay, so I conclude with that. Thank you very much.
Thank you indeed, Isabelle. Let's thank the WKFS. Wonderful series of talks. Any question or comments for Isabelle? Indeed, I have just, in the previous page, I think it was in the previous one, you emphasized that lambda should not be 1, and I couldn't see. One more, please. Yeah. Then you take the limit. It's just before this theorem.
Okay. Sorry,
you emphasize that. Yeah, here it is.
Yeah.
Why I don't see why lambda not being equal to 1 plays a role here. Because you get f equal to f. Okay.
Mm-hmm.
Okay.
Yeah, there is no contradiction if lambda is equal to 1, but otherwise you have a problem.
Mm-hmm. Okay, see it now. Thank you. Any further comments or questions for Isabelle? If not, let's thank her again.
Thank you.
Thank you. And as before, we appreciate if you share it on,
Please.
please.